Hi, welcome to Human Iris Pattern Recognition and Matching System for Unique Security Identification. I am Muhammad Abdul Khadir and this is my project for pattern recognition. Let's start with a basic description about biometric identification. It plays a crucial role in modern world security systems, and since there are infinite possible patterns, it is believed that every unique individual contains a unique biometric identifier. There are two broad categories of biometric identifiers: behavioral and physiological. Behavioral category behavioral identifiers are persistent to voice, gait, handwriting, etc. Physiological are related to your existence, such as your face, fingerprint, iris, etc. An ideal biometric identifier is characterized by three characteristics. It has to be unique, it has to be stable over time, and it has to be externally visible so that it will be captured or scanned. In this project, I will be working with human iris. A human iris is a circular diaphragm between cornea and lens. A unique iris pattern is formed during early embryonic life and it continues formation until the first year of your life. And the pattern formation is completely random. It is not governed by your genetics or any other factors. So it is believed to be unique. And it remains unchanged after the formation throughout your adult life. Also, it is a well protected internal organ, but it's externally visible so that it could be captured or scanned in security systems. So my system has three stages. Stage 1 is pre-processing, stage 2 is feature extraction, and stage 3 is matching cum training. Well, as the name suggests, pre-processing stage takes the input eye image, extracts the iris region and normalizes it to balance out limiting factors and makes it accessible or operative and for the future stages. The second stage, feature extraction, uses the normalized image and then it extracts the unique feature and encodes it into a mathematical template, which could be used as a unique identifier for the particular image. And the final stage, well, it either finds a match to the image or it could be used for training. For this project, I have used CASIA Iris Image Database version 4.0. Sorry. This is a Chinese Academy database which has been exclusively developed for iris research, and it is the 8-bit grayscale JPEG files which have been captured under near IR illumination so that all the features are clearly visible. And right now, this database is one of the most popular databases of iris images available. My system has 5 major modules. The first module is a train system module. This module is invoked when you want to train the system. So it takes the set of sample images and it extracts and evaluates or generates a template and then stores it into the database. Second module is a find match module. It creates a template of input images and then it compares the template with the reference templates in the database and tries to find out if there is a match, or if no match is found, then it returns the closely found match. The pre-processing module isolates the iris region from eye image and then it normalizes the image so that it could phase out all the limiting factors, and then it just has an image that is ready to be processed. Feature extraction module takes the normalized image and encodes into a unique mathematical template of bits or any other format so that it could be used for identification. Once an encoded template is available, it is the matching phase. It calculates the Hamming distance between two templates. The lower the Hamming distance, the more matching quotient. So it returns the closely found match upon request. The train system module, it requests for a folder which contains the sample images And once a folder is provided, it scans through all the folders and subfolders, and it tries to extract all the images. Currently my system supports only JPEG files, but it could easily be extended to support other file formats. So once the images are scanned, it invokes the pre-processing phase, which operates on those images and extracts the iris patterns and normalizes them. Then it invokes the feature extraction module, which encodes those normalized images and generates template. So these templates and the corresponding noise masks are stored in the database. The find match module, it requests for a input image for which the match has to be found in the database. And once the image has been provided, it invokes the pre-processing and feature extraction module to do the same operations just once for the current image. It stores the template and mask temporarily, not in the database, somewhere else, so that it could be compared. And then it invokes the matching module, and the matching module calculates the Hamming distance and tries to find the template with the minimum Hamming distance. The pre-processing module, well, it simply reads the input image, it isolates the iris region. Iris region is basically formed by two concentric circles, the boundary between iris and pupil and iris and sclera. So using circular Hopf diaphragm, which is very efficient in calculating and extracting geometric shapes from images, we will be able to successfully extract iris template or iris region. And once the iris region has been extracted, or then we generate normalized image and corresponding noise image using our Dogwin's rubber sheet model. Dogwin's rubber sheet model works in this manner. It creates a fixed number of radii along the iris region and takes a fixed number of data points on each radii, and this basically covers the entire iris region based on its inconsistencies, and sometimes the pupil and the sclera iris might not be concentric, so it even accounts for that. And it takes those corresponding data points, and then it arranges it in a rectangular 2D array image kind of thing. So once this is found, now every row in this particular output corresponds to one circle in the iris region. So this pretty much covers up the columns represent all the data points on particular radius, so it covers the entire iris region. And once a normalized image or a normalized output is available, the feature extraction module takes this normalized image and generates a mathematical template. The normalized image is first filtered using 1D log Gabor wavelets. It takes each row and it filters it out. So that means it takes every circular pattern and then it filters it out. And once the filtered images are obtained, phase quantization is performed on them, a 4-phase quantization, so that each data point has two corresponding bits. The four phases will be 0, 0, 0, 1, 1, 0, and 1, 1. So these 4 phases are assigned each data point a corresponding phase. So the total number of bits will be twice the normalized image resolution. So that is a decent amount of bits to operate on, and it could hold the uniqueness of a given image, given iris pattern. The final module is a matching module. This module reads the template and the noise mask from database, and then it also reads the template and noise mask of the input image. It calculates the Hamming distance, and based on the noise mask, it only takes into consideration the data points which are significant, which are not affected or influenced by noise, so that there is less error. And It returns the closely matched template and the corresponding Hamming distance. It doesn't verify whether that match is significant or insignificant. That will be performed by the previously described match module. Okay, let's see a demo. So this is my main module, and once I run my main module, it asks me a few simple questions. Firstly, welcome to iris recognition system, and would you like to train the system or find a match? Well, let's find a match. Please select an iris image to be matched, and as I said, it currently supports only JPEG file format. So okay, once you are here, you can select any image that you would like to. Let's go with the sun image. Okay, now this image is probably not in the database, so it doesn't give me a form match, or if it's in the database, it will give me a match and the corresponding image file. The database has been very extensively trained, so it would take a while to find a match. It has to scan through all the templates in the database. As I said, the match has not been found, and the maximum matching coefficient was 0.60. I'm sorry. Maximum matching coefficient was 0.6, and the closely matched template was S1001L03. So yeah, since that particular image was not in the database, it was not, the match could not be found. Let's take another image and see how that works. Let's find a match to okay, these should be in the database, so no, even this is not in the database, and the closest it could find was S1001L01, and the matching coefficient was 0.55. Okay, as it looks, the demo is quite simple, but the background work that is being carried on is quite extensive. We'll go through the code once the demo is finished. Now, in case I would like to train the system, okay, then I have to select a folder containing sample iris images. So I go to the corresponding image file, image folder. Well, let's take simple image. Okay. As you can see, it is processing the images, and it is storing these corresponding images into a database. So once this is done, we could go and check the database if you'd like to. Yeah, the images are available here. As you can see, I have been training this for quite some time, and currently there are 785 items to find a match among. Okay, let's go through the code. Well, this is my main module. Initially, it asks the user if they would like to train the recognition system or find a match. As you can see, this is option that user has to select what he would like to do. Once this is done, then you have if you choose to find a match, then we request for selecting the iris image and all the GUI. Once that is done, we would call the find match module, which would find the match for this particular input image. I'm sorry. And it returns the match template and the minimum Hamming distance value. So the minimum Hamming distance value is the one that has the closest match to the input image. So the matching quotient Well, it's 1 minus the minimum value. Since right now I'm working with very perfect, near to perfect images, I have put the threshold value to 0.09, but this could be changed in real-time applications and it would be somewhere around zero point 0.5. That is the real-time implementation. So if it is greater than 0.9, a match is found and it will display this. If it's less than 0.9, then a match is not found. However, it also displays the closely matched template so that the user could make a intelligent decision if you would like to pursue that particular image. For example, if an image has a matching quotient of 0.89, then system won't detect it, but the user will still be able to see the matching template and the matching quotient so that he could identify it by himself. This option surpasses the limitations of the system, so that recognition is not totally dependent on the system. It is monitored by the user as well. In case you would like to train the system, then it prompts for a folder, and once the folder is selected, it scans through all the folders and it goes to the train system module. And the train system module does the rest of the operations. As you can see, the train system module takes the starting folder and it scans through all the folders and the files and everything, and it goes to each file that has a JPEG extension. This could be modified, or more file mods can be added into this particular program. It could be done. So all the JPEG files are scanned, and once the JPEG files are scanned, these files are processed in a similar way by calling the pre-processing phase first and then the feature extraction phase. And the feature extraction phase does it stores the images into the database. The find match module, well, it takes the image and template and the mask, and then the image is pre-processed and the image is pre-processed and the feature extraction is done. Once the feature extraction and everything is done, then what we have next is to find whether there is a match or not, and that is done by the matching model. The clear instructions have been provided at each phase so that any new user could go through the code and easily understand it. Then we have a pre-processing phase, or a pre-processing stage rather. In the pre-processing stage, I have given a manual resolution for my normalized image, and once a normalized image is formed, this whole thing, it takes the input image, it does all the operations of extracting the iris region, then it normalizes it, it marks all the noise values, and then it just goes and performs the corresponding operations. And similarly, the feature extraction phase, it also does the same. It extracts the features and it encodes everything, and it stores the templates into the database. Matching system, it just takes two input templates and finds a match and returns the minimum matched value. These are the extension files. A canny edge detects the edge, circular edge area, and then thresholding of the edges, and then isolation of the irises. All this could be done. These are the sub modules that support the main module functionality. So here are a few suggestions for the future work. Well, currently I'm working on ideal dataset So if you would like to deploy this particular system into the real-time application, then you need to have a little more sophistication around the edges to make sure that it works properly. And the filter parameters right now, the log-Gabor filter parameters, they have been founded by trial error, and the optimal values have been manually or hard coded to be but these filter parameters can be dynamically calculated with respect to the database, because when the database changes, these values change. And the matching quotient, even the threshold that I have shown you was at 0.9, which is a pretty high threshold. This is not the case in real-time applications. It has to be around the mean value, 0.5, 0.6. That should be good, but it again is dependent on the database. As database gets populated, the threshold should be high so that it could reduce the number of false identifications. And finally, well, during the training phase and the matching phase, the training phase actually takes quite long time. So it is recommended that you could perform some matching algorithms simultaneously. But since the database is being updated, this is not a simple operation to just perform two things at one time. But there is a possibility that you could try and try and make the system work in both modes at the same time. The training could be performed in the background, and the matching algorithms could be operated in the front ground upon the request of the user. Thank you. Thanks for watching the demo.